Hi, I'm GUO CHENG GUANG, topic of Primary 6 from Amy Primary School. For this time, we're still at ordinary differential equations. While ordinary differential equations, we still have many more other methods. But right now here, first we'll still use all these methods that we have used before, and let's try to revise a little bit. Okay, so let's start from the first type of this ordinary differential equation that we had. Y prime plus, for example, just px, and here times the actual y. And for this first order, linear and homogeneous. Now this first type that we've learned is very simple. We just use the separable ordinary differential equations. Next, we move on. We change this a little bit. For example, we can change this 0 into qx. Now just take note of this. Px and qx are both functions of x. So then for this right now, first order, still linear, but non-homogeneous. And for this type, well, still very simple. We use the integrating factor, or the integrating factor, or the if. Then next we move on a little bit more. Here we times y to the power of n. And what happens here? First order here is non-linear. Then here is non-homogeneous. And did you realize what type of ordinary differential equation is this? It is for these lessons, the type of ordinary differential equation that we have. And for this type of ordinary differential equation, the name we gave to it is the Bernoulli equations. Okay, this is called the Bernoulli equation. And for these different types of methods, whether how we could use these methods will go by exemplification. But in this exemplification, we can have many different types. For example, including trigonometry, inverse trigonometry, those exponential, and a lot more others. Okay, so let's look at what we have this time. So this example over here, it says y prime, which means y first derivative minus. Okay, so here is a very long fraction. Okay, so over here, this whole fraction I already written it down. Then for the next part, which will be equal to, here is another part. Okay, we have something like this. Now at first we said, we might have some like trigonometry, but what type of it is here? Well, this is actually hyperbolas. And this, well, you might seem familiar that at first this part might be like cosine or sine. Well, but you have this extra h at the back. For example, cosine with this extra h, you can say as hyperbolic cosine. Then the sine with the h, you can say as hyperbolic sine. Okay, then next for this part. Similar to those trigonometry, they do have identities, and we're going to use some of them today or in this lesson. So first part here. Okay, this second part, you have 3. Okay, we'll just split it into like 1 and 2. Since 1 and 2 is 3. But you might ask, why are we using this? Why can't we have some other ways? Okay, well, I'll show you a little bit of something else later. Then from this part, here is also 3. So I'll also split it into 1 and 2. And after that is all these things. Okay, then from here, I'm going to factorize a little bit. Okay, here we could factorize this hyperbolic cosine x. Now that here will be square of this. Then here we'll have square of the hyperbolic sign. Then for this part, we still have another part at the back. Then from this part, you can factorize this hyperbolic sign. Okay, then at this part, we'll just be writing down the others. Then next from this part, now in the trigonometry, you do see something similar. Sine square plus cosine square. Now in this hyperbolic of this trigonometry, you also have something. You have the square of hyperbolic sine x plus the square of hyperbolic cosine x. Now for this part, it's actually something a bit of difference, because if there's not hyperbolic, then in the trigonometry it will just be 1, but now it's not. It's also not -1. By something else. Is hyperbolic cosine 2x. Now for this formula, you can call it the double arguments for this hyperbolic cosine. The next part, the other part we are using is here. Let's take a look. 2 is hyperbolic sine times hyperbolic cosine. Now in the trigonometry, you also have something similar to this. And this is actually the double arguments for hyperbolic sine. Okay, so let's first convert these. Okay, I don't think it is bracket. After it's this part. Okay, so I might want to write this in order for later. And this part is what you get. But when we look at this, are we just jammed here? Are we just stuck? But wait, let's take a look. This hyperbolic cosine, hyperbolic cosine, hyperbolic sine, and hyperbolic sine. Wait, if it is not hyperbolic, then in trigonometry we do have something similar. Co, sa, sa. But in this hyperbolic, well, trigonometry do also have this thing. Well, we do have it. Okay, let's see for this part first. This hyperbolic cosine. Okay, for example, you can take this part as x. Then you take this part as y. And this part, okay. If we take something like this, then after that, what you'll get is this hyperbolic cosine with x plus y. Wait a second, here's not sine. Okay, this is hyperbolic sine. So still you have to be very careful about these. Okay, so this we have figured out for this first part, which is in the numerator. The next part will be for this denominator. Okay, the next part, this part is different. This is hyperbolic sine. Then we get x plus y. Now there's a little bit of difference from the trigonometry. In trigonometry, if it's cosine, then it must be the opposite. For example, positive, then in cosine, is negative. So here is a little bit of difference there. Then for this next part, okay. So what would you have? Hyperbolic cosine x plus y, which is a 2x plus x. So that means it is 3x. Then for this part, also x and 2x. So it's hyperbolic sine 3x. And then there's a y. And just start it like this. See, you can actually simplify from this, which looks very, very complicated. You just, first thing, you can try to simplify it. Simplify into the simplest form. But then, do you think this space is enough? Obviously no. So, I'm going to erase these parts first. Now that I write it down again. So what kind of substitution do you make here? So in this Bernoulli equation, your substitution will be let u be y to the power of 1 minus n. Okay, you get this. One minus n. So here's the 1 minus 3. So you get negative 2. So y will be u to the power of negative 1 over 2. Then after that, here you have your y prime. So y prime would be negative 1 over 2. Then u to the power of negative 3 over 2. Then of course, your first derivative of u. So it'll be like this. But before I erase this, I might want to write it down somewhere. Well, I won't tell you why I wanted to write it down first, but later on, you'll find out. But this later on doesn't mean right away. Okay, so erase this part. Okay, next, we want to try to make something which we know how we can solve it and which methods we can use. Now, what kind of methods have we used before? How about let's change this into u first derivative or u prime. Negative, that means all these positive, except for this part, which will become a negative instead. 3. Okay, this is the first part, you get something like this. After a negative, then here half, which means times 2. So here, you get negative 2. Then these other parts, some stay the same. This u, gone. Because we times u to the power of 3 over 2 on both sides. So So that means here, this bracket will also not be needed. Okay, so this is what you have. Next, what do you have? Wait, let's take a look at the changes that has happened. At first, our ordinary differential equation. First order, non-linear, non-homogeneous. Next, breakdown, first order, linear, non-homogeneous. Then we should change from a non-linear ordinary differential equation into a linear ordinary differential equation. Okay, and that's what we have. So that means right now, at this point of time, we can use the integrating factor, or the IF. Then at this part, this hyperbolic cosine, you put it into the dx. Well, of course, this 3 also bring along inside. After that, what did you realize? This part, what if you just take it as y? This part, what if you just take it as y? dy over y? Isn't that simple? Is the log, or the natural logarithm. Here is the exponential. Here is logarithm. In fact, natural logarithm. Don't they just cancel out? So this is what you get at last. The hyperbolic sine 3x. Okay, so that means we times this integrating factor on both sides of the equation. So then this is what you get. For this part, you can first have total differentiation. Then this part, you have that dx. That means here you also need a dx. Now, since you have this dx, so that means you also can integrate. Okay, this part, well, I'm just going to write it like this. The part we need to work out is here. We need to work out this part. When we work out this part, what can we use from here? Can we use anything? I think so. This 2, you have that hyperbolic cosine, you have that hyperbolic sine. Okay. So that means it'll just be that hyperbolic sine. So that means you will get like this. Wait a second. I think you still need something. Well, why do you still need that something? here you integrate already, right? Since you have integrated one part already, that means you need to have that integrating or the constant. So you can put it as C1 over here. Then after that, here you can straight away integrate. And you'll get this C, this exact C. Wait, and this part, sine, this part is something similar to those of the trigonometry. Hyperbolic sine becomes hyperbolic cosine. So same thing, hyperbolic cosine becomes hyperbolic sine. Okay, so next part, u. U, now what was u at first? Okay, u is y to the power of -2. So that means you can divide this to the other side. Okay, you have something like this. Next, you still need to find y. But beware, here is 2. That means you need positive, negative. Then from here, what next? You already got your y. Since you already got your y, but are you really sure that this y is the correct solution? How about let's verify it? Okay, let me show you this way of verifying. Wait, just straight away use this part. Okay, wait for a moment. This verify thing, I'll move it to somewhere else. Perhaps this whole part. Okay. Well, this part you can use verifiable as verify is a verb. You can also choose to use this is the verification. Well, there's a little bit of English usage here. So from here, let me just write this whole thing down. Then both sides you differentiate. So I have something like this. Next part, let's just straight away find out y prime. Okay, so this negative can cancel out with this. So then it will become 1 over 2. Then this 1 over 2 you still have to contain these. So that means you have this part. Then here you still have your y cube. Okay. You still have your y cube. Next part, what would you have here is, let's take a look. This part. Try to make some changes here. Here, negative plus 3, then 3 over 2. Now 3 over 2 here we already have it. Okay. Then from this part, wait, how about let's try to change it back inside here. This part and this part. So you get one of this. But wait a second, you have another of 3. So that means you only have 1. Okay, now what's left? This hyperbolic cosine, then 3x, and one of these hyperbolic sine, then 3x. So from this part, hyperbolic sine 6x. How about we just use this? Here is 6x, so here is 3x, 3x. That means it cancels out with this. And you'll be left with hyperbolic cosine 3x. Like this. Oh wait, would it be confusing if you put like this? Is y cubed inside this hyperbolic cosine? So we'll just put brackets for this, okay? Next part. Let's just combine these together. But you might just be wondering, wait, why are you just only combining them together instead of just like straight away trying to get this? Now this is when this part actually comes in use. Because if you compare it with this part, you actually realize that it's pretty much the same. And this part, it comes from there. So that means for this, part, you can straight away write it as that. Okay, now this is what you have. Since you get this part and this comes from this. And to get this part from the original ordinary differential equation, it's just using some of these identities. Okay, well, I'm not stopping you from doing that. You can go on with that method if you want. So that means just making a little bit of conversions, like you can move this part to the other side. Okay, they'll make a quick comparison between what you get and the original ordinary differential equation. Then you realize they're actually the same. So when you realize that they're the same, that means it's correct. Okay, so for this lesson, I'll just end it here. And for all of these, I hope that you can understand it so far. So if you like our videos, don't forget to subscribe to our channel. We'll see you in the next lesson. Thank you for your watching.